Okay, then welcome back again. And so this week, in this week, in this week's session, we will be discussing about the integral form of the momentum equation, of how and its various forms, say its indicial form, its vector form, and how to obtain the. Basically, we discuss about the derivation of Navier-Stokes equation, or the final form of the Navier-Stokes equation from the linear momentum conservation. So we'll briefly discuss that or look into it. Just few steps and just see how the final equation is obtained. What are the assumptions that have been put in the Cauchy's momentum equation or the Navier's equation that gives us the final form of the Navier-Stokes equation. So we look into those assumptions, and I feel like you have watched the week 11 lectures very properly, because these week's lectures are more of conceptual ones rather than rigorous calculations like the last week sessions, which were very long lengthy calculations. But this week's session would be more on the conceptual, more towards the conceptual part, and getting those concepts clear would be the primary goal of today's session, or in a correct way, revising those concepts taught by Professor Chakraborty would be the primary goal for today's session, and assign and problems also. So I guess I am clear. So again, I will just briefly go through some of the points. So in any point of time, if you are unclear, you can just stop me and say like why have you taken this assumption, or why you are telling this. You can just stop me, and meanwhile I also would ask some of the doubts. So you should answer and so that this session becomes a dynamic one rather than a monotonic. So I guess I'm clear. So yes. So okay. Okay. So the integral from the momentum conservation, again, from the linear momentum conservation, we again take two assumptions. First is the stationary frame of reference and a non-deformable CV. So I guess you know the implication of both of these assumptions. If you don't recollect, or you're slightly confused, you can ask me. But I would again suggest you to go back to the lectures or the lecture notes, so that would be very clear. So that's fine. Again, this is the linear momentum conservation equation. I guess this was rigorously discussed in the last week sessions. So for a non-deformable and a stationary control volume, we can say that say because of the non-deformable control volume, we can take the time derivative inside the integral. So this is what we have done, and for a stationary control volume, the relative velocity becomes equal to the velocity of the incoming fluid. So taking those assumptions, we obtain this form of the equation. And again, since I also discussed regarding the types of forces that can act on the control volume, and both of you rightly pointed out that there are surface forces and body forces, and we discussed ample amount of examples regarding the surface and the body forces. So again, we looked into this the concept of traction vector in the first problem solving session itself, and also Professor Chakraborty briefly discussed about the concept of traction vector in the initial lectures as well as this week's lecture. So I don't think I would like to go back to these concepts back again, so to save time. But still, if you have any doubt, you can just mail me or ask questions in the discussion forum. So that's fine. And then again, the expression for the body forces was derived like this, in this form. That is the integral over the control volume for for the, say, Vi is the body force per unit mass, then you can obtain the net body force acting on the control volume by this integral. And so the left hand side of the equation, that is the summation of forces, the inertial forces that act on the some of the forces that act on the control volume can be given by these two integrals, and the right hand side is again the expression that we had obtained from the Reynolds transport theorem. So we again implement the concept of Gauss divergence theorem that gives us a relation between a surface integral and a volume integral. So I guess this conversion is the concept behind this conversion is clear. So it's clear, right? The Gauss divergence theorem, how we obtain this. It's a basic transformation, I guess. That's clear, right?
Yes, sir.
Okay, thank you. So we have to apply the Gauss divergence theorem in both the LHS and the RHS, because we want to convert this surface integral from the left hand side and the right hand side the volume integral. So we apply the Gauss divergence theorem to convert these integrals. So consequently we will have a divergence term on both the sides, as you can see. So, and since this integral, all the terms have volume integral over a certain arbitrary small control volume, so we can take the integral out, and as you know, for integral to be 0, the integrand must be 0. So that's why given that this would be our integrand, we obtain the final form of the Navier's equation or the Cauchy's momentum equation. Okay, so right now up to this point there are only two assumptions that we have taken. First is a stationary control volume and then non-deformable control volume. Up till now we haven't taken any assumption regarding the fluid being a Newtonian one or non-Newtonian one, the flow being incompressible or compressible. We haven't taken any of such assumptions. Okay, so this equation, the Navier's or the Cauchy's momentum equation, has a very wide approach, or is a very general form of the momentum conservation. And after taking some certain assumptions only, we obtain the Navier-Stokes equation, the well-renowned Navier-Stokes equation. So this part you should be clear. Okay, we haven't taken any such assumptions to such as incompressible, compressible, or Newtonian or non-Newtonian fluids. Okay, we haven't taken any such assumptions. So this is a very general form of the momentum equation. So that's why it is known as the Cauchy's momentum equation or the Navier's equation. Okay, so I guess this form is clear. Okay.
Yes, sir.
Yes, you can still see we have a on the right hand side we have a body force term, which cannot be actually simplified further depending on what kind of body force that governs or is predominant in a certain problem. We substitute that in the body force term. If it is gravity, then we substitute it by gravity, or if it is electromagnetic forces, we substitute it by electromagnetic forces. So that is there, but you can still see here that we haven't substituted any simplification or to the stress term, to the shear stress, to the stress term. So the real simplification of this form of the equation comes when we find a relation between, say, the velocity gradients and this shear stress term. Okay, so if you could recall, could any one of you please tell me the relation that we initially used in our previous problems for shear stress? Like, say if you can tell me in the index notation. Okay, say if we want to write in shear stress, initially we actually wrote this. So what was tau ij equal to in terms of index, in terms of velocity gradients?
Mu into
Yes, please.
dou u by dou y, sir. Dou u y.
Okay, in terms of index notation. Okay, so I guess it was something like this. And moreover, I also insisted you to divide the term by 2, uh, and in some, and there was some discrepancy regarding this division by 2 was there or not. So I would say that from my perspective, like what I have learned or I have read, we insist on dividing this factor by 2, but I would say this won't make any much of a difference, okay? In terms of, say, it will just be a scalar multiplication by a factor of half, okay? So that won't make much difference. The most contributing factor is the gradients that we take. The gradients of velocity that we take along a certain coordinate direction, okay? Say, this is very important that in for certain problem, okay, del u by del y may be much larger than del u by del x. So rather, whether we should take del u by del x or del u by del y, that's what makes more difference or more error in our calculation, rather than including a factor of, including or disregarding a factor of half, okay? That's why I'm saying the comparatively insignificance of this addition of a factor of 1 by 2 in the expression for tau ij, rather than emphasizing more upon the expression or the index notation of the velocity gradients, okay? Say del ui by del xj and del uj by del xi, because if you write del ui by del xi, this makes a complete it's a complete different expression compared to del ui by del xj. So that's what I'm emphasizing more upon these notations, okay? So you need to be clear. Okay, so from this Cauchy's momentum equation, say if you recall the index notation as taught by Professor Chakraborty, if I say I equal to 1, then ui is equal to u. So for a 3-dimensional coordinates, for a 3D system, I can take the value from I 1 2 3. So ui basically will take so ui can basically denote u1 u2, I'm sorry, u1 u2 and u3. Basically it denotes the velocity along the three velocity along the 3 coordinate direction, okay? And it can be Cartesian, cylindrical or spherical, depending on what type of geometry we are dealing. So the coordinate system may change, but the index notation or the vector form of these governing equations are independent of the coordinate system that we are choosing. So that's why these are very much universal compared to the special form of the equations that we derive for certain coordinate systems. Say it is a simplified form in the Cartesian coordinate system, and that's why you're dealing with terms such as tau xs, tau xy, and dou by dou x, dou by dou y, these terms, okay? So Cartesian coordinates, say Cartesian coordinates, okay? Okay, so now as I told, the simplification of the Cauchy's momentum equation comes by simplifying the stress terms or shear stress term in terms of some velocity gradients, okay? Because we want to reduce the number of unknowns in our governing equation, and if we leave this tau ij term as it is, this creates another, say the tau ij vector would have its components such as it would be a 3 cos 3 tensor, right? So it would be tau 11, tau 12, tau 13, then tau 21, tau 22, tau 23, tau 31, tau 32, and tau 33. So if we leave this form of the shear stress term in our governing equation, we basically are left with 6 more unknowns that are tau 11, tau 12, tau 13, then tau 22, tau 23, then and tau 32. And assuming that we are considering the what to say, that tau ij equal to tau ji, that comes from the angular momentum conservation for in an elemental volume in a fluid flow. Assuming that this assumption is valid, we are now left with 6 additional unknowns along with u, v, w, and what is the another unknown?
Rho.
Rho. Okay, and if I say it is constant, then one more unknown is left, I guess. P, right? Pressure. Is that clear, Priyanka? How pressure is an unknown here also? Is also an unknown, right?
There is no pressure term, sir.
No, not right now, but eventually it will come. Say if we simplify it, there will be a pressure term, right? Yes, that only I'm thinking in that sense. The final form. Actually, you are rightly pointed it out. It is not initially here, but eventually you will see you will have to deal with pressure. So there is unknown known as pressure also. There will be pressure will also be an unknown term. Okay then. So now you know why it is very important to represent this tau ij in terms of other variables in the flow field in the fluid flow, and so that's clear, right? Why you want to eliminate these unknowns, tau ij terms, right?
Yes, sir.
Okay. So what we do is we dissociate the tau ij into tau ij hydrostatic and tau ij deviatoric. Okay, and I guess then by name itself makes the concept clear. Hydrostatic means that the shear state that would act in the fluid flow given the case that the fluid is at rest. So the only stress that can act in such cases are normal stresses, and basically that is pressure. But the term deviatoric itself basically means that the shear stress, actually this term may be derived from the term deviation, which basically means that any stress that is generated because of the deviation from the state of rest of the fluid. Say whenever the fluid is in motion or it is not at rest, there will be some additional stresses that will be generated, and those stresses are considered within the umbrella of tau ij deviatoric. So that's why this is also included. So I insist that you remember this equation forms because at the end we need to take the sum and to get the final form of our constitutive relationship. Okay, so again if you recall, I guess there was a expression like such as Cij KL, it was EKL, like that. If I am wrong, you can please correct me. Was there form like this, form of the relation between the shear stresses and basically this is the velocity gradients? This was the expression, right? In the video lectures. The thing is, the constitutive relationship basically gives us an expression for this shear stress term tau ij in terms of the velocity gradients. Okay, and this term EKL basically means, can anyone of you please tell me what EKL would denote? Okay, so basically it will again denote del u k by del xl plus del ul by del xk. Okay, it's basically again the rate of shear strain. So mu term will cancel, I am sorry. So it will basically give us half of del uk by del xl del ul by del xk, the rate of shear strain. Okay, shear strain, not the shear stress. Shear stress comes when we add that factor of we multiply it with dynamic viscosity. Okay, so it basically gives us this. Okay,
sir,
okay,
EKL is half of, sir,
is EKL is half of del UK by del XL
Yes.
plus del UL by del XK, sir.
Yes.
It is the rate of deformation.
Yes. Shear strain.
Yes, sir.
Yes. And it will be equal to shear stress when you multiply with the viscosity. And the viscosity term. So it will become shear stress then. That's why I removed the viscosity term here. Okay. So this basically means this. So what the considered relationship does is that we want to form a relationship between the shear stresses, that is tau ij, and the shear strain. Okay, rate of shear strain in the left hand side. So this mapping between two tensors, right? We want to obtain a relationship between two tensors, two second order tensors. And if you rightly recall, I told that in the first problem solving session itself that the mapping between two second order tensors would be done by a fourth order tensor. SoCijkl is basically a fourth order tensor. Okay, and I won't go through the detailed derivation of this relationship, the final form of the equation, how Professor Chakraborty derived taking certain assumptions and certain concepts of tensor calculus, and he obtained the final expression given by this equation. So I won't go through it. I insist you that you go through it once again because it is a very time consuming and very heavily conceptual topic. But rather I will just say that he in there also he took certain assumptions such as tau aj be symmetric. This was one of the assumptions, and the other two assumptions were that the fluid flow is fluid flow is homogeneous and isotropic. Okay, these were the other two additional assumptions. So given these assumptions, he obtained the final form of the equation given by tau aj equal to minus p del ij plus lambda ekk del ij plus 2 mu eij. So can anyone here please tell me again just what del ij refers to? It has a certain name.
Kronecker delta.
Okay. So what is its property?
When I equal to j, it is 1 equal to 1.
Okay, when I
It
equal
equals
to
1, 1. Yes.
okay, it is 0 when I not equal to j. Right?
Yes, sir.
Yes, sir.
Okay. So here you can, and again I actually accidentally pointed out. I wish to ask you, but I accidentally pointed out. The P del ij terms gives us the hydrostatic part of the shear stress, and these two terms lambda ekk del ij plus 2 mu eij basically gives us the deviatoric shear stress, that is shear stress because of the motion of the fluid. So this was the final constitutive relationship, and here now you can see, right, Priyanka, that we are dealing with another unknown, that is pressure, right? So again this pressure term becomes an additional unknown. So by removing these additional 6 terms of tau 11, tau 12, tau 13, tau 22, tau 23 and tau 23 and tau 33, we are left with one additional unknown along with the velocity components u, v and w, and now we are left with another unknown, that is pressure. Given considering that rho is constant, that the flow is predominantly incompressible. Okay, so these are the 4 major unknowns that we have to deal with. Okay, so okay, I guess this part I don't need to extensively discuss, that how the del uk by del xk basically means it gives us the divergence of the velocity field, and this gives us the rate of volumetric strain. Okay, so I don't think I want to I need to discuss it again. So it basically means that this expression gives us the mathematical significance, the physical significance of this mathematical term is given by this, like the divergence of velocity field gives us the volumetric strain of the flow field, and this term, the second term, gives us the rate of angular deformation, that as Augustus rightly pointed out. So I don't want to discuss it again because it's just a repetition of what we discussed. Okay, so now again I need to write the expression. If I'm wrong in any of the steps, you can please correct me. Okay, the final expression for the constitutive relationship, it was, I guess, tau ij minus p del ij plus lambda again, okay, del u k by del x k del ij plus 2 mu eij. I guess I have not made any mistake. So right. See, the tau ij hydrostatic term is given by minus p del ij. Okay, so that's clear. Where this p is the thermodynamic pressure. Okay, right? Now for the rest of the part, that is the deviatoric part, tau ij deviatoric, and as you can clearly see, since it is a second order tensor and it has two indices, two free indices, you can see that it will generate a 3 cos 3 tensor, right, which would have 9 elements, right? So what we are now interested is that only the diagonal elements of this 3 cos 3 tensor. Okay, so it would basically mean the tau 11, tau 12 and tau 13 term. Oh, sorry, I made a mistake. Tau 11, tau 22 and tau 33 diagonal elements, right? The diagonal elements of the deviatoric stress tensor. Okay, so if we substitute I and j with 1, 2 and 3 respectively, so if I equal to j and we substitute by I equal to 1, I equal to 2 and I equal to 3, you will get these expressions. So you can just clearly check how I have derived, and if I have done any mistake, you can just point out. Okay, I guess it is clear. So okay, so now after getting this expression for tau 11, tau 22 and tau 33, what we do is we add all the diagonal elements and divide this term by 3. So what we basically did is tau 11 plus tau 22 plus tau 33 divided by 3 would be equal to by 3 would be equal to minus p plus lambda plus 2 by 3 mu del u k by del x k. So is it clear how we obtain this expression, right?
Yes, sir.
Yes, sir.
Okay. So now what we say is that the sum of the diagonal elements, or basically a trace of the stress tensor, divided by 3 would give us the mechanical pressure denoted by minus pm. Okay, and in principle pm and p are two different entities. Okay, why? Because as pointed out by Prof Chakraborty in the lecture, the mechanical pressure denotes the translational mode of energy of the molecules. Okay, but a thermodynamic pressure constitutes the translational, the vibrational and rotational, all modes of energy molecules. Okay, generated because of all modes of pressure generated because of all modes of these energies in the fluid, translational, vibrational and rotational. Okay, but the mechanical pressure is solely because of the translation mode of energy molecules within the translation mode of energy of the molecules within the fluid flow. Okay, this is the general difference, and in principle, and as you can clearly see by this mathematical expression, these two terms pm and p are not equal, and there is an additional factor of lambda plus 2 by 3 mu del uk by del xk. Okay. So now what happened is that now we impose a certain hypothesis known as the Stokes hypothesis in the governing equation. Stokes hypothesis says that Pm would be equal to P given that lambda plus 2 by 3 mu is equal to 0. And lambda, this basically means that lambda will equal to minus 2 by 3 mu. Okay. Lambda would be equal to minus 2 by 3 mu. So this will be the Stokes hypothesis. This is a very important hypothesis or a very important step in the simplification of the Cauchy's momentum equation, or one of the major steps for obtaining the Navier-Stokes equation from the Cauchy's momentum equation. Okay, so this is one of the assumptions that we take, the Stokes hypothesis. Okay, first assumption. Suman these are basically, I briefly discussed about two cases where Stokes hypothesis are valid. So Professor Chakraborty mentioned that okay. So he briefly discusses about the relaxation time. So is there any doubt regarding the concept of relaxation time, or I need to discuss it a bit? It's basically a time required for a system to change from one equilibrium state to another when imposed to a change through some external means. Like say the fluid is subjected to some force. Okay, this force would create certain deformation within the fluid particles, and this deformation would cause, say the fluid was initially at rest and say the fluid was initially at an equilibrium state, and because of the imposition of these external forces, the fluid undergoes some deformation or motion as it may happen, and it reaches another equilibrium state. And this equilibrium state need not to be like very temporarily very far apart. Like the equilibrium states can be infinitesimally close. Like the equilibrium state may change from one point to another, and the time frame or time gap between these equilibrium states may be very small. Okay, so this is also a very important concept to be clear about. It need not to be that I impose a force and the next equilibrium state that the fluid flow will reach is after 1 hour. It need not be the case. Okay, so given this concept, he said that if the time required by our fluid flow, the system is basically our fluid flow or the control volume, the fluid within the control volume, is the time required for the system, the control volume, to change from one equilibrium to another is is smaller than the time scale of the imposition of these external forces, then the Stokes hypothesis holds good. Is that clear? The red line that I have written. Say, in general, relaxation time for most of the fluids is smaller than the time scale for a change of properties. So it basically means that if I impose a external force, and it will take some time to impart the change in the fluid flow, and if the fluid automatically achieves or reacts to this change and attains the next equilibrium state before the time frame of the imposition of these forces, then I can say is that the Stokes hypothesis will hold good no matter what the condition or the property of the fluid is. Like the fluid may be incompressible or compressible, I do not worry about that. But if the relaxation time of the fluid is smaller than the time scale of the imposition of our forces, then I can say that the Stokes hypothesis holds good. So this is one of the very important factors for the wide generality of the application of Navier-Stokes equation, because in most of the cases, as I just clearly pointed out, in most of the fluids, this case is valid, that the relaxation time is much smaller than the time scale of the change of properties. Okay, that would basically change because of the imposition of some external forces. Okay, because of this validity, it's only the Navier-Stokes equation is applicable for most of the fluid flows. Okay, So this is the important this is an important assumption, and as it is, and the next assumption is that, so see, since the, okay, let me discuss the next assumption. And again, for an incompressible flow, the divergence of the velocity field would be 0. So this part is, I guess, this assumption, I guess, I need not to discuss or derive how we obtained it. Okay, this is basically from mass conservation. So is that clear? How we obtain for incompressible flows del dot v is equal to 0, nebula dot v is equal to 0. I don't think I need to derive it, right?
Yes, sir.
Okay. So given these two assumptions, okay, first is the validity of the Stokes hypothesis, and second is incompressible flow. Okay, these two cases. So now you can see is that this expression would basically can basically be written as minus Pm equal to minus P plus lambda plus 2 by 3 mu nebula dot v. Okay, I guess it's clear. So either in this case, if the Stokes hypothesis is valid, then this term would be equal to 0, right? In that case, again, minus then in that case Pm would be equal to P, right?
Yes, sir.
Or else, even if the Stokes hypothesis is not valid, and if I say that the flow is incompressible, then again the Stokes then again we can find that Pm is equal to P, right? So the satisfaction of either of these conditions would give us a conclusion that the mechanical pressure is equal to thermodynamic pressure. And why Stokes hypothesis is why the knowledge of Stokes hypothesis important is because it is a more general case compared to the incompressibility of the fluid flow, because it's a very rare, it's a very crude assumption that we take that the flow is incompressible, which is basically a very crude and hard and fast assumption that does not take into account for most of our common fluid flow problems. That's why to take into account more general cases, we need to know the validity of the Stokes hypothesis. And since the Stokes hypothesis is valid for most of the fluid flows, that's why we can apply the Navier-Stokes equation, or we can apply our Navier-Stokes equation even in the case when the flow is not that we cannot in the cases where the flow cannot be assumed primarily incompressible. So even in that case, since because of validity of the Stokes hypothesis, we can obtain the final form of the Navier-Stokes equation from the Cauchy's momentum equation. So now I guess you know what are two assumptions that we took, right? The Stokes hypothesis and the incompressibility, either of them needs to be valid. Okay, so I'm like, again, I want to apologize from my side that this week's topics are like very heavily conceptually heavy. So I might fail in explaining some of the concept very clearly. So you might stop me whenever you require and just ask me like, I didn't understand this. You can please repeat it. Okay. So yes, now what we do is, since we know the final form of the stress term, that is from the constitutive relationship, we substitute the tau ij from the constitutive relationship to the Navier's equation or the Cauchy's momentum equation, right? So this is basically the final form of the shear stress term, right? What we discussed. This is basically that. So after substituting that, we simplify the terms a bit. The left hand side remains the same. This term, I should write it, I guess. Del by del xj of minus p del ij becomes minus del p by del xi. This I'm just asking out of curiosity. Okay, do you know like how we derive this? I'm asking like how we obtain minus del p by del xi from this term, from the left hand side. Do you know this one, this relation?
When I equal to j, no, sir?
Yes, del ij. This term, like how we obtained this from this expression, do you know?
When I equal to j.
No. Need not to be I equal to j. It's just a general identity or rule in the tensor calculus. Okay, that's why I just wanted to know whether you know it or not. Even if you don't know it, that's fine, because it's a little bit, it's a, I can say, a postgraduate level concept. So I don't emphasize both of you to know about it, but still it's a very simple calculation. Is basically like if I denote the partial differential operator as, say, del j, because it's divided by del xj, so I just since it is del by del xj, I denote it by del j. Okay, it is minus p del ij. So since p is a scalar, so I can take p out, and it basically mean del j by del ij. So in this case, if it is the case, like the differential operator has j, and since the differential operator has a j term, and the Kronecker delta has del ij, and so in this expression j becomes the repeating index, right? So what we can do is we can just eliminate the I am sorry, I cannot actually take the p out, so actually it will be operated upon, so I'm sorry. So what we can do is we can remove the repeating index and just keep the free index, okay, in this expression. So what will you get if you remove the repeating index? Is the step clear, both Augustus and Victor? Like, I don't want you to know, but just I'm telling you the steps. Like, it's not important for you to know right now, but just the steps, how we obtained it. Is that clear?
Somewhat, sir.
Okay, like it's understandable. Like, you can see a similar.
Yes.
Yes.
No, I have to rewatch the video again, so then I think it will be understood.
Okay, that's fine. Okay, I can again show with another example, the second term itself again. So again, the second term, say, the second term is given by del xj. Okay, the second term, this one, 1, 2, and 3. The second term, it would be lambda del uk by del xk. Again, a Kronecker delta operator, right? So what I can do is I denote this del by del xj by del j, okay, in terms of the free index that the coordinate axis terms has. Okay, so what I can do is it will be del ij, then I take the Kronecker delta here. I can play with it since it is just an operator, so I can take this here, and the final term upon which the final expression of the final term, that would be the multiplication of this partial differential operator and the Kronecker delta operator, upon which the upon the product of the partial differential operator and the Kronecker delta operator would operate on this term within the brackets, right? So it would basically be lambda del uk by del xk, right? So what I told is that if we encounter such expression, a product between a partial differential operator, that is this one, and a Kronecker delta, so what you need to do is, in this case, you can remove the repeating index term and substitute the free index to the partial differential operator. Okay, so it will basically mean, it will become del I lambda del uk by del xk. So it will basically give us del by del xi lambda del u k by del x k. So this is what it is. Okay, so you can repeat it as you said, and so the similar process, similar steps you obtain for a third term also. Third term does not have a canonical delta, it seems, so it's not complicated, but still we simplify the expression by operating the partial differential operator on the third term also. So the final expression that we gain is that the right hand side, left hand side remains the same that we obtained from the RTT, so that need not to be repeated, but the right hand side becomes minus del p by del xi plus del by del xi in bracket lambda plus mu del uk by del xk. So this would basically be the divergence of the velocity field plus del by del xj mu del u by del xj plus rho bi. Okay, this is just a simplification of this term. Okay, it's not that difficult, it's very simple. Now since we know, now what we want to do is we want to impose our Stokes hypothesis, right? So from Stokes hypothesis, what we got is that lambda is equal to minus 2 by 3 mu, right? So we substitute lambda is equal to minus 2 by 3 mu in this equation. So it will basically give us mu by 3, and again so I can write this, the final form would be right, just the right hand side, it would be minus del p by del xi plus del by del xi mu by 3. Say I want to write it in this form, plus del by del xj mu del ui by del xj plus rho bi. So this is clear, right? How we obtain this final expression from this equation. It's clear, right?
Yes, sir. Yes, sir.
Okay. Again, we want to briefly discuss about the assumptions that we take. First is stationary reference frame, then a Newtonian fluid, and a homogeneous isotropic fluid. Okay. Now see, this assumption was initially taken while deriving the linear momentum, the Cauchy's momentum equation from the linear momentum conservation, right? So this we know how this assumption is useful in our derivation. Okay. The homogeneous and isotropic fluid assumption we take, if you recall, from the final derivation of the constitutive relationship from the fourth order operator. Like basically, like we derive tau ij is equal to c ij kl e kl. So you will see the usefulness of the assumption of homogeneous and isotropic fluid in simplifying the fourth order tensor to the sum of second order tensors for deriving the final form of the constitutive relationship, that basically becomes minus p del ij plus lambda del uk by del xk, del xk del ij plus 2 mu eij. See, we initially had a fourth order tensor, okay, and so it would be, this fourth order tensor would basically have 81 elements. So now you can understand, if we have 81 elements in a stress tensor, how complicated the mathematics would be to derive each and every term of that tensor, right? So it's very complicated. So we take certain assumptions, as I pointed out previously, symmetry of the shear stresses because of the angular momentum conservation, tau ij equal to tau ji. Then we take another two assumptions, that is the homogeneous and isotropic fluid, to obtain this form of the constitutive relationship. And now, can any one of you please tell me, where do we use the assumption of Newtonian fluid in this expression? Newtonian fluid.
So when you substituted tau is equal to mu into dou ui by dou xt.
Okay, so basically it is the third term. Okay, because the third term basically gives us the relationship, if you can recall, yes, the third term basically gives us the relationship between the rate of shear strain and the shear stress. And for Newtonian fluid, if you recall, I told that tau ij is equal to 2 mu Eij. This was a Newton's law of viscosity, right? If you recall.
Yes, sir.
Yes, and since this is valid for only Newtonian fluids, this is substituted here, so we can get the final form of the constitutive relationship. Okay, so now you know why these assumptions are important and how important the roles are for simplifying the Gauni equation, because in principle you can clearly see that the Cauchy-Moulton equation is unsolvable, right? Because of tau, we don't know the expression of tau ij. Only after we know the final expression for tau ij in terms of the pressure or the velocity, pressure and the velocity gradients, then only the number of unknowns are reduced to 4. As you can see there, clearly see there, u, v, w and p, right? And again we encounter a problem of that we do not have an explicit equation for pressure. Right, say I just want to ask, like if you have a system of 3 simultaneous equations, okay, if you have a 3 unknowns to find, say x, y, z, so basically you need 3 equations to find the value of x, y, z, right? You know that
Yes,
concept,
sir.
right? For the equation to be, what to say, solvable, I actually am missing that particular term, like the system equations is, I'm sorry, I'm forgetting the particular term, particular mathematical term that tells whether the system is solvable or unsolvable, so that I'm forgetting, but still you know the concept, like if there are 3 unknowns, then you need 3 equations to obtain the value of these 3 unknowns. So even if now we have 4 unknowns and 4 equations, basically we have the 3 what are the 3 equations? Basically the linear momentum conservation equation in the 3 directions, along the x direction, the y direction and the z direction, right? We have those 3 linear momentum conservation equations. And what other equation we have? Additional equation?
Mass conservation.
Yes. So x, y, z momentum conservation, and the 4th equation is mass conservation. So in principle the system of equation that we have must be solvable, right? Because we have 4 equations and 4 unknowns. But still the issue is for incompressible flow is that we have no explicit equation for pressure. This is not the case for a compressible flow field, because you know that for a compressible flow field, the expression for pressure, we get the expression for pressure from the equation of state, that is P equal to rho RT. We have an explicit equation of pressure for a case of compressible flow, but in terms of incompressible flow, we don't have an explicit equation of pressure. So again, that is an additional issue. But still, if we say that I got the term. Even if we said that the system of this system of equations are consistent, like I guess now you remember, now you understand, right? Consistent and inconsistent system of equations, right?
Yes, sir.
Yes, I recall it now. So
Yes, sir. Yes.
yes. So even if this system of equations are consistent, 4 equations and 4 unknowns, so this is solvable. Mathematically it should be solvable, right? What do you say?
Yes, sir.
Yes, sir.
Yes. But still I can say that nobody has till now solved the Navier-Stokes equation completely in a 3D flow field, having giving the expression for the u, v and w velocity components and the expression for pressure. Till now nobody has solved it. And if any one of you are very interested in fluid mechanics or a mechanical engineering domain, you will know that the Clay Mathematical Institute had awarded a $1 million, I don't know the prize money, but a very huge cash amount plus a Nobel Prize for anyone who solves this Navier-Stokes equation for 3D in a 3D coordinate system and gives the expression for the u, v and v velocity, u, v and w velocity components and the pressure. Whoever does it, he will get a Nobel Prize. But still nobody is able to do it, even if the system of equation is consistent. So can you, any one of you please tell me why is it so? You got my question, right?
Yes, sir. Don't know, sir.
Don't know. Okay, Augustus, can you give? Do you like to give a try?
No, sir, I too don't know, sir.
Okay, fine, fine, it's fine. It's understandable that you don't know, because I also didn't know initially. Because I also was told by my professor that this is solvable, but nobody is able to solve it. So I was also doubtful. Still, the thing is that the main I can say the main culprit behind the unsolvable nature of this equation is the non-linear nature of the equations. Non-linear. Again, out of curiosity, I would say this is a very simplified form. Okay, it is the Navier-Stokes equation along the x direction. It is a Cartesian coordinate system. So can any one of you please, and again let's take mu equal to constant. Okay, I don't have the final form now. Mu equal to constant. Okay, so basically this mu will come out of the differential operator. Okay, so that's why I'm just simplifying you. Okay, so in this equation, okay, in this equation, this is the linear momentum conservation along the x direction. Okay, so in this equation, which is the non-linear term? I told you that non-linearity is the main issue behind the unsolvable nature of these equations. So in this equation, which term or which terms denote non-linearity? Again, beforehand, do you know the concept of linearity and non-linearity of equations? Like definitely you must have dealt with it in your maths course. Like you're given some equations and you have to say whether these equations are linear, non-linear, otherwise, like transcendental forms of governing equations, differential equations are also there. So are you aware with those concepts of linearity and non-linearity?
Sir, is it? I'm not sure that that product of dependent and its differential should not be there. Is it like that?
Yes. Even if you say that, that's correct. So can you please tell me what are those terms here?
Sir, uj del ui del xj term, sir. That which is coming on the left hand side next to del ui del t.
This
Those
one.
three terms. Yes, sir.
This one, and this one, right?
Yes, sir.
Yes, absolutely correct. So Augustus rightly pointed it out. These terms are the main culprit behind the non-linearity of this equation. So Priyanka, given that you have correctly pointed out the definition, so you are clear, right, why these terms are non-linear?
Yes.
Yes. So you will eventually see that I don't know whether you have attended the week 11 lectures completely, because I also haven't completely covered it, the exact solutions of Navier-Stokes equation, because I hope that you attended the lectures. You eventually see that for all those exact solutions, given that the flow is steady, so with the flow is steady, this term will go to 0. In all those exact solutions, you can see that these terms never come into picture. These terms, one way or another, tend to 0. You will see that the exact solution that you solve are primarily one-dimensional, so V and W component goes to 0. Moreover, you take a fully developed flow case in most of the cases, so the del u by del x terms goes to 0 even if you have some positive value for u. So in those cases, you can see that efficiently the mathematical assumptions that we take eventually makes the left hand side to be identically equal to 0, and that's why we are free from any non-linearity that could mathematically make the problem intractable. So now we are only left with some second order linear terms, given that if mu is constant, so that makes the equation solvable, and that's why we can get some special cases of the solution for a Navier-Stokes equation, that is known as the exact solution of Navier-Stokes equation. So these are only what we basically deal with. So now you know, right, why it is difficult, why it is unsolvable till now. And what is the, and this basically is the what to say, gist or crux of the whole fluid mechanics. Like whenever who can do this has completed or learned everything there is to know, that we need to know in fluid mechanics. I can say almost everything, because again they are non-Newtonian fluids, right? That again complicates the problem again. So yes, there is lot to learn, but I guess I was able to tell you about the both the interesting and the complicated nature of fluid mechanics through this session, because this session was very important or very necessary for you, both of you, to know, because this gives a basic idea or basic, it acts as an introduction to the concept of fluid dynamics. That is the more advanced version of the basic fluid mechanics that we have dealt with. It gives you a basic introduction to the concept of fluid dynamics that you will eventually deal when you go further deeper in the in this subject. So I guess I was able to do it. So is it clear up to this point? Like,
Yes, sir.
okay, and
Yes.
okay, and again, like both of you, do you feel like encouraged, or like now at least have a bit different perspective that you initially had about fluid mechanics compared to the previous lectures? Now do you understand why the mathematical fundamentals are very essential for understanding the subject of fluid mechanics, right?
Yes, sir.
Yes.
Yes, sir.
Okay, thank you. So see, I almost covered what to say, consumed one and the 70% of our today's session, discussing a lot more on the concepts rather than solving problems, because this week's problems are very heavily conceptual based. So I needed that both of you are conceptually clear before attempting those problems. Okay, that's why I put on so much time while for discussing the concepts. And since both of you are clear till now, I feel that both of you won't be finding any difficulty while tackling the questions that we are going to discuss in today's session. Okay, so I don't think there is any problem, any issue regarding there will any issue regarding solving those problems. So let's directly go through it. Okay, so these are very trivial questions but heavily conceptual. So if you know the concept, you know the answer. Okay, so right. Okay, so let me read the first question to you. Which among the following is the correct mathematical form of the angular momentum principle for a fluid flow in the absence of any body couples? It's a very trivial question. I discussed this, I guess, 2 or 3 times in this session, so I think both of you can easily answer it. So what's the answer?
D, sir.
Augustus? Augustus, what do you feel?
I have no idea, sir. I have to think and tell, sir.
Okay, that's fine. Actually, I discussed it quite a lot in today's session about the angular momentum conservation for a fluid flow. Actually, I don't think sir has discussed about this derivation, so I'm not completely sure whether they have discussed it or not. But still, Priyanka has rightly pointed it out. So for the conservation of angular momentum, this is one of the what to say, fundamental conclusion that we reach into while deriving the conservation of angular momentum for a fluid flow or for a fluid element. What we basically do is that we take a say a square fluid element, okay, and say there will be some shear stresses acting on each of its faces. So what we basically do is that the summation of all the moments, I should write M, would be equal to I alpha, right? That is the net. That is a moment of inertia and the angular acceleration. So from this expression, after solving, say if it is del x and say if it's del y, it is tau 1 to tau 2 1. So after deriving or after going to certain derivations, you need to take an assumption of that del x and del y, since it tends to 0, it's very small, then del x and del y would also tend to 0, right? The product of very small terms will lead to further smaller term, like 0.01 into 0.01 would give us a further smaller term, basically 0.0001. So it will be much smaller than the product of the individual numbers, more smaller, it will be smaller than the individual numbers itself. So given this assumption, you finally lead to a conclusion that for such cases you will have tau 21 is equal to tau 12, sorry, tau 12 is equal to tau 21, and this is basically the conservation of angular momentum. So angular momentum because like I also know that we haven't discussed about the crude derivation of the angular momentum conservation starting from an elemental fluid element. Like we haven't discussed about it. We just briefly talked about the angular momentum conservation from the perspective of RTT. So it's understandable that you do not know the expression, but this is what it is. Okay, this is actually
Okay, sir. Thank you.
conclusion of the angular momentum conservation. Okay, thank you. So let's go to next question again. It's again very simple. For a compressible flow of a homogeneous and isotropic Newtonian fluid of dynamic viscosity mu, obeying Stokes' hypothesis, the components of stress tensor are given by, I guess it is like what we discussed right now itself. So it shouldn't be very challenging. It is told that flow is compressible. You need to take into consideration that it's compressible, not incompressible. Compressible, homogeneous and isotropic, trivial, Newtonian, again you know what terms may come into picture, and Stokes' hypothesis is valid. I can write it down. This lambda is equal to minus 2 by 3 mu. So given these assumptions, what will be the constitutive relationship for the stress tensor? You can just briefly go back to your notes, or even if you were writing a bit when I was discussing regarding these equations, you would be able to answer it.
Answer B, yes, sir.
B. B or D?
Yes, sir.
B.
B, sir.
Okay.
Yes.
Augustus tells it is B. So Priyanka, what do you think?
B, sir.
B. D.
Not D, sir. B.
B. Okay. So again,
No, sir. Actually, not sure, sir.
why? So I guess it's very
The
simple.
third term, sir, I got
Okay.
it.
Third term, right? Third term was, I guess, as far as I can remember, it was tau ij minus p del ij plus
Was it
lambda.
plus 3 by 3 or?
I'm writing it, plus 2 mu eij, right? This is equal to 1 by 2 del ui by del xj plus del uj by del xi. And I said, it is said in a question that the Stokes hypothesis is valid. So lambda would be equal to minus 2 by 3 mu, right?
Yes, sir.
So given this, what would be the correct answer now? this would basically, it is basically del dot V. Now you just need to substitute so right on the screen itself.
The last options.
Yes, it's all same, just in it, this was actually lambda. Instead of lambda, you need to substitute in terms of mu. So it is D. So Augustus, is that clear?
Yes, sir. Yes, sir.
Okay, sure, no problem. It's, again I said, it's very conceptual one. Like either you know it or you don't know it. It's conceptual. You need to remember. So that's why I emphasize a lot this while discussing. So that's understandable. That's fine. Okay. Again, this is a very interesting question. Let's go through it. Consider the following statements. For an incompressible flow, the mechanical pressure is equal to the thermodynamic pressure, irrespective of the validity of the Stokes hypothesis. Okay. First statement. Second statement is, for fluids undergoing rigid body motion, the mechanical pressure is equal to thermodynamic pressure. Rigid body motion, mechanical pressure is equal to thermodynamic pressure. These are the two statements. So given these two statements, we have four options. So which of the following options are correct? These are two statements.
Sir, option B.
B.
Yes, sir.
One is false, two is true. So Augustus is saying it is B. So Priyanka, what do you suggest?
So one.
Sorry. One is true. Yes.
So what do you say, Augustus? Which is correct?
Yeah. I did not notice the term incompressible flow. For incompressible flow, irrespective of the validity of Stokes' hypothesis, mechanical pressure will be equal to thermodynamic pressure. So option one. So one is true. And for fluids undergoing rigid body motion, can it be considered as an incompressible flow, sir?
It need not to be incompressible flow, but the rigid body motion would imply certain factors, or it will lead to certain case by which you can say that, by which you can simplify the constitutive relationship, which would simplify the constitutive relationship. So I need to know what term does it simplify, like what terms get eliminated or what terms get added or what terms is modified.
There will not be rotation. The only translational will be there, no, for under rigid body or rigid body motion. So mechanical pressure will be equal to thermal. So both are true, sir.
Okay, you are saying C. And
C.
And Priyanka, what do you suggest?
So one is true. I think two is also true, sir.
Why do you think so? Because Augustus has kept his point of view. That's correct. But why do you think so that 2 is also correct? Rigid body motion. Yes.
I think in rigid body motion there will not be any shear stresses.
Okay. Why? Why so?
Because there is no acceleration in rigid body motion.
Okay, so it is correct. Yes, like there will be no shear stresses. So basically, since there are no shear stresses, and see, I believe I discussed about boundary layer theory a bit, and how it is the existence of shear stresses and not the absence of dynamic viscosity that determines the potential flow region and the boundary layer region, right? I told you that after a certain length, that is a boundary layer thickness, the velocity gradients are so small that the shear stress cannot manifest themselves, right? Because of the absence of velocity gradients, and that's why basically the flow becomes inviscid after a certain region. So in that perspective, now you know the importance of velocity gradients. So here also he rightly pointed out, there is no fluid without viscosity. Every fluid is viscous. It may be small, it may be large, but every fluid is viscous. But it is the existence of velocity gradients that manifests the existence of shear stresses. And in this case, as there are no shear forces, and it is because of the fact that there are no velocity gradients in the case of rigid body motion. And if there are no velocity gradients, you can clearly see that these two terms, the del uk by del xk, this term and Eij term, both will be equal to 0, right? Since there are no velocity gradients.
Yes, sir.
Yes, and in that case, if you sum this up, since it is still in initial form, you need to add them up, and if you add them up, you will finally see that the mechanical pressure will be equal to the thermodynamic pressure. So both other statements are correct. Okay. Okay. So
Okay, sir.
both of you are correct in this case. So okay. So question number 4 is quite a bit lengthy one, I cannot say. You can actually just look into the final expression of the velocity profile and just tell me the answer. So just asking, have you gone to the lectures that discussed about co-ed flow?
Yes, sir.
Who said yes, who said no? Like, I was just confused.
I said no, sir.
Okay, Augusta said yes, right?
Yes, sir.
Okay. And then I think Priyanka won't be able to contribute much for this question, but since Augustus you have gone through the lectures, I believe you know. I don't encourage you to get to the final form of the. I don't encourage you to derive the entire derivation again, but can you just tell me the final form of the velocity profile in this kind of flows? Pressure driven co-ed flows. Pressure driven co-ed flow.
Final form of the
Velocity profile. It was something u by u tau, as sir has discussed, like just like what sir has discussed. So what was it equal to? Tell me the final expression, that's all. Was it something like this? Augustus, was it something like this? Where alpha was equal to h square by 2 mu u tau minus dou p by dou x. Okay, since that's fine, like if you couldn't find the expression, but you have gone through it, so you know the concept, right? That's fine if you can't find the expression, that's fine. As far as I can recall from Professor Chakraborty's lectures, I think this was the final form of the expression. We may see like if it is wrong or right after going through the solutions, so that's fine. Okay, so you don't need to find it, and that's fine, maybe it is the expression. Okay, so since you have gone through the video lectures including co-ed flow, can you tell me what co-ed flow actually is, what actually means? So I will tell you one example. No, I will tell you an example.
bearing. It's a flow between the bearing and the shaft. Okay.
Oh, okay.
Application example.
Yeah, that's correct. But tell me the basic what to say, geometry, flow geometry for a co-ed flow. Like, say what happens is that for a flow between two parallel plates, I say that there are two plates that are infinitely large, where both of the plates are stationary, and there is a flow between these two parallel plates. So this we tell as the flow between two parallel plates, or plane Poiseuille flow, if you can recall. if you recall, or you will eventually encounter. But for the case of coed flow, as you rightly pointed it out, it's flow between a bearing and a shaft, and it's very important in the domain of fluid mechanics. And it has, since it has the application is bearings, which is an integral part of any industry. So that's fine. But can you define me the geometry, the flow geometry? What happens? Here also I see there are two plates, but is it how it is different from two parallel plates? Is the upper plate moving with certain velocity and the lower plate stationary? Right?
Yes, sir. Are you asking something connected with fully developed flow?
No, I'm just asking about coed flow. What is coed flow?
Quite.
Yes, it's fine if you cannot define, because it's understandable. These concepts are very basic but difficult to grasp at one go. You need to revisit again and again, and I don't know how many times I have encountered or studied coed flow to finally get the gist of it. So it's fine, no problem. Okay. Since you rightly pointed it out, its application lies in the ball bearing or ball bearing and shafts. Okay, so that's fine. So in the case of coed flow, shear driven coed flow, it is in this case the lower or the bottom plate remains stationary. Okay, one of the plate may remain stationary, but in my case I am saying the bottom plate remains stationary. So the velocity of the bottom plate is 0. Okay, and for coed flow, the upper plate moves with a certain velocity, say u or u tau, whatever may be the case. Say it moves with a velocity u tau, and the motion of this plate generates a velocity profile of this form. Of this form. Okay, a linear velocity profile. I guess I had discussed about it also in some of the previous lectures, like in the case where the gap between the box or the fluid film layer is very small, you can assume a linear velocity profile. Do you recall?
Yes, sir.
Yes,
By
something like
solving
yes.
problems, viscosity problems.
Yes, exactly like that. So in the case of coed flow, that was basically coed flow. So in this case, the expression for coed flow is given by u tau y by h. This is the velocity profile for a simple coed flow. Okay, so and here there is no applied pressure gradient. So del p by del x is equal to 0. So it is the motion of the moving plate, in this case the plate and upper plate, that generates the flow. And as you said, Augustus, regarding shaft and bearing, okay, I will zoom it in to clarify it. Say if this is a shaft and this is the bearing, it is the shaft and this is bearing. So when the shaft rotates with certain velocity, what would happen is that it will generate a velocity profile, which will obviously in this case will not be linear. It will generate a velocity profile of this form. Okay, it is not linear. Is it visible in the screen?
Yes, sir.
Yes. So the rotation of the shaft would mean that the shaft is rotating with certain velocity, say omega r, and this rotation generates the fluid that is stuck with the shaft rotate with the similar velocity, same velocity omega r. Okay, and what would happen is that the fluid that is connected with the outer bearing is stationary. So this will generate a similar velocity profile to the one that we see in the case of a shear driven coed flow. These two phenomena are exactly the same, just the geometry is different. In this case we deal with a cylindrical coordinate system, a cylindrical geometry. This is a Cartesian one. In this case, if I recall, I'm forgetting the exact expression, but in this case also the velocity profile has an expression of the form of this. where A and B you need to find. I may be wrong, okay, I'm sorry. So you need to find the expression, the value of A and B in this velocity profile for the case of flow between the shaft and the bearing, okay. So these two cases are exactly similar, but the physical principle that governs the flow is the same, but just the geometry is different, okay. Both are shear driven, okay, shear driven. Now it may happen that along with the motion of the plate there might be an additional pressure gradient that drives the flow, okay, because in the case of pipe flows or flow between two parallel plates, it is the pressure gradient that drives the flow, right, if I'm not wrong.
Yes, sir.
Yes, that is the pressure difference between the two ends of the pipe generates the flow or pushes or initiates the flow, right. It is pressure driven. In the coed flow also, it may also happen that there is an additional pressure gradient, a favorable one, say, that drives the flow in the required direction that we want, and there is a motion of the upper plate. The upper plate is moving with a velocity u, as it is mentioned here. So now there are two factors that drive the flow. So in this case it becomes a pressure driven coed flow. So I will make the geometry quite simple. So it will be u equal to 0 and u equal to u. Capital U. Okay. Priyanka, is this concepts clear? The geometry and the flow. Okay.
Yes, sir.
So what I will do is, I won't go through the derivation because it's quite not that extensive but quite time consuming, and we need to cover up 6 more questions. So I don't think time will permit us to go through derivations, but still they have mentioned in the question that we define a non-dimensional pressure gradient given by P equal to h square by 2 mu u minus dp by minus dou p by dou x. Okay, so in terms of these factors, since since one of you is not clear or do not know the concept of coed flow, I would write the final expression of velocity gradient myself. The final expression for the velocity gradient uy is given by P y bar minus y bar whole square plus y bar, and here again it is u bar. See, this bar denotes non-dimensional terms, okay, non-dimensional values. So u bar basically means small u, that is the velocity profile. The velocity profile basically it is denoted by u by y. So small u by capital U, okay, and y is given by y by h. Y bar is given by y by h. So this is non-dimensionalized. So I don't think both of you have gone through the concepts of non-dimensionalization, right? How to non-dimensionalize the equations. You have not gone through it, right? Or do you know about it?
Numbers we have seen it in some examples when we derive Froude's number and Weber's number.
Yeah.
So, not.
Okay, no, that's fine. For fluid mechanics also, it's exactly the same. So here also we'll briefly discuss it. It is the final week's topic concept. So we'll briefly discuss about non-dimensionalization, how to non-dimensionalize, how to take the non-dimensionalizing term, like with respect to which value we need to non-dimensionalize our velocity or pressure or coordinates, the x, y and z coordinate direction. So we will briefly discuss about it. But say in this case I'm now explicitly saying that I am taking u bar as small u by capital U, where capital U is the velocity of the upper plate, okay, and y bar is equal to the y direction coordinate y by h, where h is the gap between the two plates. So I have mathematically modeled the whole problem. So only you need to only deal with these equations, okay? Specifically only this equation, nothing more, okay? Priyanka, is it clear? Is the equation clear?
Yes, sir.
And the capital P is this one, okay? Don't confuse yourself with it is the pressure. It is actually non-dimensional pressure gradient, okay? This P is given by this. Okay, so if the problem is set in mathematical model, so let's go through some.
Sir,
Okay.
Sir, excuse me.
Yeah.
Sir had derived it as u is equal to 1 by 2 mu
Wait.
dp dx
1 by 2 mu dp by
into
dx.
dp dx
Okay.
and y square minus yh
Okay.
plus u1 y by h.
u1 y by h. Right.
Yes, sir.
See,
Yes, sir.
this is basically the same equation. We have just, if you substitute the value of p here, this equation is basically in dimensional form, okay? It is dimensional form. What we have done is we have non-dimensionalized the equation, and if you substitute this expression for p in this equation and u bar equal to capital U by small u and y bar equal to y by h, you will get the same equation. Is that clear? This equation is in dimensional form, okay? Basically superposition of a pressure driven flow and the shear and the co-ed flow. This equation is also the same, just showing us in the non-dimensional form, okay?
Okay, sir.
It's basically the same. If you substitute, you will get the same equation. You just need to, we have just non-dimensionalized it, or we have just mathematically manipulated it, okay?
Okay, sir.
Okay. Well, in some sense I am doing it because it makes our calculation much simpler, because the questions that we are going to deal with, we need to deal with some derivatives, some substitutions. So if we keep it in non-dimensional form, it simplifies our calculation a lot. That's why I am doing that. You can keep it in the dimensional form also, but it may become quite difficult to handle. That's why I am writing it in a non-dimensional form. You will eventually see its importance. So okay, that's fine. So let's see question number 4, and we have to now run through these questions very quickly because only 8 minutes are left, and I have some interesting results to show to both of you. Okay, the resultant assertion and reason type question. Okay, the assertion is that the resultant velocity profile will be a linear superposition of a simple co-ed flow, purely shear driven flow, and a plain Poiseuille flow, purely pressure driven flow. Basically what Augustus has correctly mentioned, this is the plain Poiseuille flow, velocity profile for a plain Poiseuille flow, and this is the velocity profile for a shear driven co-ed flow, right? This is one assertion, okay? The reason is that this superposition is possible because the non-linear convective acceleration is 0 for both simple co-ed flow and plain Poiseuille flow. This is what they are giving the reason behind the possibility of superposition of the both velocity profiles. So, which of the following options is correct? I guess we just now discussed about the difficulty in solving the Navier equation, where the non-linearity lied, and how the removal of those non-linearities simplified the equations a lot. That's why we could.
Sir,
Okay.
So
sir,
both
excuse me,
are
sir.
true.
Assertion A is true.
Okay. Okay, that's your answer. And Priyanka, what do you suggest?
So both are true. Like what you said just now, based on that. I said.
Okay, and but both are true in available both here. So either A or B.
First one.
First one, okay. So right now we have discussed. See, I guess you just need to go through or just look into whenever you get the chance, or you will eventually read about the differential equations, or and how you. I guess say if you get a differential equation, you know that if say a what to say, if e to the power x and e to the minus x are both the solution to a governing equation, then a e to the power x plus b e to the minus x, thus this sum is also a solution of the governing equation, given that the equation is linear. Okay, so keeping this concept in mind, since our equation is linear, why it is linear? Because the non-linear convective acceleration terms, u del u by del x, v del u by del y, w del u by del z, these terms are equal to 0. That's why it makes our governing equation linear. Governing equation linear. And same you will see with the boundary conditions. And since the governing equations are linear, you can apply the principle of superposition, right? What we basically did is that this velocity profile we decomposed as a sum of the, I will draw it separately, okay? Sum of a linear simple shear driven coed flow and a pressure driven plain Poiseuille flow. So the black one, this black one is basically the sum of the red and the blue velocity profile, okay? And why we were able to do it? Because our governing equations were linear. And why they were linear? Because then all the non-linear terms, that is u del u by del x plus v del u by del y plus w del u by del z, these non-linear terms that lie in the convective acceleration terms were 0. See, it is quite difficult to make you understand by just saying if like you have not gone through the expression or derivation of the coed flow problems or Poiseuille flow problems. And I suggest that since Priyanka you haven't gone through it, you go through it once, okay? Like given you understand the concepts that I told you in this class, you just try to relate this with the lectures that you eventually see, and you easily understand what I am trying to say, okay? How the linearity of the problems, linearity of a differential equation helps in writing the solution is a superposition of the of all of its possible solutions, okay?
Yes, sir.
Okay, that property that we have applied, that is what we have applied, okay? Linearity of our linearity of our governing equation, which is a basically second order differential equation. Okay, Augustus, is that clear?
Yes, sir.
Okay, so okay, we go to question number 5 then. Which among the following statements about the resultant velocity profile is or are correct in the case of a favorable pressure gradient? This is basically P greater than 0. Which of the following statements are correct? We have u of u of y is equal to P y bar minus y bar whole square, y bar square, sorry, plus y bar. So favorable pressure gradient. So can any one of you please tell me what do you mean by favorable pressure gradient?
P1 minus minus P2 is positive, sir.
P1 minus P2 is positive. Okay. Okay, that's correct. So it basically means that if P1 minus P2 is positive, it basically means that del P by del X would be negative, right?
Yes, sir.
Yes.
Yes, sir.
Okay. So okay. So that's correct. So if the pressure at the inlet is higher than the pressure at the exit, say 1 is the inlet and 2 is the exit, then the higher pressure will drive the flow from the higher pressure region to the lower pressure region. And this basically means that our flow is approaching to a lower pressure region, and thus moving in a direction that is desirable to our needs, right? We want the flow to drive from point 1 to point 2, and that's why we want the pressure at point 2 to be lower than point 1, so that the flow drives from point 1 to point 2. And that's why, since this condition is favorable to us, favorable for our use, that's why we tell this kind of pressure gradient as favorable pressure gradient. Okay. So del P, dou P by dou X is equal to, is negative in the case of favorable pressure gradient. So okay, this is actually a bit you need to do certain calculations and substitute certain values of capital P. So it's not that difficult. Again, for favorable pressure gradient, I can say if okay, I will write it. Favorable pressure gradient means that dou P by dou X is negative, and simultaneously dou U by dou Y should be positive, or it is dou U by dou Y greater than 0. So just as a hint, since you don't have an expression for pressure, explicitly you don't have an expression of pressure gradient, because in this equation all terms are non-dimensionalized, you can take the help of this expression. Basically, del U by del Y should be greater than 0. And it is given that P is greater than 0. So given these two conditions, which of the following cases or following statements are correct?
Option B, sir. The velocity decreases monotonically from U at the moving plate to 0 at the stationary plate.
Okay. Is only that correct, or are there any other options that can also be correct?
Sir, is it both B and D?
B and D. B and D.
Yes, sir. Yes, sir.
Okay. Okay. So this is what it is, your answer. So Augustus, what do you suggest? Are both B and D correct?
Sir, if the pressure gradient is favorable, it means that it is not a quiet flow, isn't it, sir? Because for quiet flow, the pressure gradient is 0, isn't it, sir?
Yes, but
Need not be.
yes, but our case is pressure driven quiet flow, right?
Yes, sir. Yes. So in that case, it seems B and D are correct, sir.
Okay.
Or oh, yes sir, B and D are correct sir.
Okay, so let me also check. I forgot the solutions, but question number 4. So yes, I guess it is correct. Both B and D are correct. Okay. So yes, this year got it correct. So it's basically you just for right now you just what to say, take into the mathematical consideration, like just take consider the problem to be mathematical without considering the physical concepts. Later on we'll see what physical implications does it have on the velocity profile, so we'll see it later. But right now you can just take the solve problem mathematically, okay, without keeping much emphasis on the physical significance, just for right now. Okay, now let me read to question number 6. Which among the following statements about the resultant velocity profile is or are correct in the case of an adverse pressure gradient? Similar case to previous one, but now it is adverse pressure gradient. P0 basically means dou P by dou X is positive, or dou U by dou Y bar is less than 0. Same approach, what will be the conclusion?
Sir, seems all the options are correct sir.
Okay, you say all options are correct, so maybe I need to discuss with you regarding the derivations, but still, what do you think, Priyanka? Okay, so I think I need to revisit. Okay, for right now you can solve question number 6, but
Sir, I think C is correct.
okay. Velocity profile decreases monotonically from U at the moving plate. Okay. Is it the only correct option, or there is some other correct options as well?
I don't know about the rest.
Okay. So actually, for question number 6, options C and D both are correct, and I am really sorry. For question number 5 is actually question of option B and C that are correct. Okay. Regarding question number D, like, it's interesting. Could any one of you please tell me how did you find that option D was correct? Like, it's necessary for me to also check. Like, okay, can you please tell me? For question number 5, P greater than 0. I guess you took the derivative, right? P 1 minus 2y bar plus 1. Okay, for P greater than 1, you said that the velocity decreases monotonically from U at the moving plate to 0 at the stationary plate. See, this option, like, visually also cannot be correct. Why? Because you can clearly see in this velocity profile, the velocity has a maxima somewhere between the plates, right? If you draw a straight line, you can see this is a point where the maximum lies, right? This is not the maximum velocity, maximum velocity, right? So option D should visually also cannot be correct. So that's why option D is not correct. Okay, question number 5, option D is not correct. Is that clear why option D is cannot be correct?
Yes, sir.
Okay. Could you check question number option number C instead, putting a value of p greater than 1 and C, or just take a certain value of p, equate the expression to 0 and find the expression for y whether it lies between the plate or not. I'll just try it myself. Okay, say p equal to 2, say, then it will basically mean 2 minus 4y plus 1. Then I equate, to find a maximum velocity, I equate the derivative to be equal to 0. Okay, so I have 3 minus 4y bar equal to 0. So it basically gives me y bar equal to 3 by 4, which is 0.75. So it basically tells me that for p greater than 1, where I have taken p equal to 2, I have a maximum velocity at a point y equal to 3 by 4 or y bar equal to 3 by 4 or 0.75, which is in between 0 and 1. Okay, and you will see eventually while you play with the value of this p that is greater than 1, you will eventually see that the maxima shifts from one point to another. This basically I mean is that, since if you can see that this point, say point 1 is maximum for a certain value of p that is greater than 1, if you change the value of p to some certain other values, you can see that you will eventually see that the value of this maxima shifts from one point to another. For certain point, this will be the maximum velocity, like the velocity profile may look like this. So it will go to this point and it will again decrease to 0, or in some cases it may be the point of maximum velocity. So velocity profile will go from here, reach the maximum value, sorry again wrong, go from here, reach the maximum value, and then again monotonically reduce to 0. Is that clear, like how playing with different values of p will give you different velocity profiles? In all those cases, if you have a favorable pressure gradient where p is greater than 1, capital P, okay, not pressure, capital P is greater than 1, you will get a maxima at a point which lies between y bar equal to 1 and y bar equal to 0. Is that clear?
Yes, sir.
Okay. See, it is difficult to understand right itself, because you need to play with various numbers of p to get to a final conclusion. And that's why I had some results at the end, so I will show you that, but right now we can just solve the questions. Okay, so 6 is also similar. I don't emphasize you to repeat the same again. Okay, so let's go to question number 7. This is again an interesting question. Find the value of p for which shear stress on the upper moving plate vanishes. Tau at y equal to 1 equal to 0. So it's very simple, I guess. I will just show you the clues. You can tell me the answer. Question is clear, right? For what value of p the shear stress at the upper moving plate becomes 0? Is the question clear? Both of you? Augustus and Priyanka, is the question clear? Question number 7.
No, sir. For me, I need little clarification, sir.
Okay, sure. Then I encourage you, right? If you have any doubt, please ask me. Okay. See,
Okay, sir.
there are two plates. One is stationary, one is moving. We have certain velocity profile. This u has some velocity, and here u is equal to 0. Here y bar equal to 0. Here y bar equal to 1, because it is non-dimensionalized. Okay, this is the velocity profile. So because of this motion, the motion of the flow between these two parallel plates, there will be a shear stress at the lower surface of the upper plate and the upper surface of the lower plate, basically in these regions. In these regions there will be some shear stresses, right? Why? Because of the motion of the fluid between these plates. Okay, so the questions here, and there is some pressure gradient. Again, there is a non-dimensional pressure gradient that I mentioned here, that is being applied between this region. So question number 7 asks us that what is the value of this P, that is the non-dimensional pressure gradient, that would make the shear stress at the surface of the upper plate to be equal to 0. That shear stress at this point would be equal to 0. Then what is the value of P for this case? Is it clear now, Augustus?
Yes, sir. Clear, sir.
Okay.
At the value of y equal to 1, y bar equal to 1, we have to find.
Yes, that's the catch. Substitute in this expression itself. I have solved it half through. Expression itself, substitute y by y bar equal to 1. Then equate it to 0. Find the value of P.
So minus 1, sir.
1.
Okay, now I am confused. 1 says minus 1, 1 says 1, but let me check. Let me do it myself here. So if I equal to 0, then P is 1 minus plus 1 equal to 0. Then because minus P plus 1 equal to 0, then P is equal to 1. P will be equal to 1. Okay,
Yes,
Augustus, is that clear?
Sorry. Yes, sir. Yes, correct.
Okay. Again, exactly same question. Now they are just asking what will be the value of P for which the shear stress at the bottom stationary plate vanishes. Just substitute y bar by 0, then find the value of P in this expression itself.
Minus 1.
Again, it's very trivial. It's minus 1. Is that clear, Augustus? Why it will be minus 1?
Yes, sir. Clear, sir. P plus 1 equal to 0, so P equal to minus 1.
Yes, exactly. Okay, so this question is the last question for today's session, and it's quite interesting. They have asked us is that find the value of P for which there is no net flow through the channel. Okay, let me ask you, like, even if in what scenario do you feel that the flow between the channel would be equal to 0?
So when it is not moving,
But again, there is a pressure gradient that may drive the flow, right? Even if the upper plate may not be moving, the pressure gradient that is between the two plates will drive the flow, right?
sir, if we equate the pressure gradient and the velocity of the plate, then will it be 0?
To what? Equal to what? 0 or what?
No, equating the velocity with which the upper plate moves to the applied pressure gradient.
But they are, both of them are generating a flow towards the positive x direction, right?
Then we should apply external force.
Then it makes the problem a bit more complicated, right? It's a very simple concept. I guess sir has discussed in the class regarding that. So, okay, Augustus, could you tell us like what term, like what will be the case when the net flow through the channel is equal to 0? Because there's no point of equating the velocity to be equal to 0, right? It is a it is a variable that is changing from each point from 0 to 1. It is changing from point to point, so we need to equate from each and every point. You need to equate the velocity to be equal to 0 to get a 0 net flow. Then you can say that the net flow is 0 if velocity is 0 at all the points throughout the channel width. That may be one case, but that is again what to say, will not say, like even if we have velocity profile as u bar is equal to p y bar minus y bar squared plus y bar, even if you are here equating it to 0, you are left with two unknowns, right? Pressure, and mathematically if I am looking into it, p and y bar, so this becomes again in mathematically intractable, so this doesn't make any sense. So what is that we need to that what we can do to simplify the expression also, and physically make the also give a correct explanation for which the net flow through the channel would be 0. Augustus, can you tell something about it? This is the last question. So again,
should we find du by dy equal to 0? We will find one. We will come to know whether it is maximum or minimum, sir.
No. Del u by del y basically give you the orientation of the velocity profile, right? If it is positive, then basically it means that the flow will tend to move in the positive x direction. If it is negative, then the flow has a tendency to bend towards the negative x direction. Okay.
Okay, sir.
That is the case. So it does not give us a very true mathematical idea behind whether the net flow through the channel would be equal to 0 or not. So since we are time bound, let me give you a conclusion is that in this case what you need to find is that the net mass flow rate or the volume flow rate through the channel should be equal to 0. In that case only the net flow through the channel will be equal to 0, right? Basically you're even given a term flow. Whenever you're given the flow, you need to understand that it's something related to the mass flow or the volume flow rate. Assuming that rho is constant, I will say that net flow would be 0 when q equal to 0. Am I correct? Like if q equal to 0, then the net flow would be equal to 0?
Yes, sir.
Okay. Then how we obtain q? Would be integral of 0 to 1, say if it is non-dimensional, u bar dy equal to 0. Correct?
Sir, correct, sir.
Okay,
Integral 0 to h u dy equal to 0, sir.
Yes. Then just substitute the expression for u bar. Dy. So again, I can do the integration, but I need to show some results also, but it's very simple. If you simply do the integration as I have done here, is it visible, this part? Right? If you simply do the integration and substitute the value of the limits, you will find that p equal to -3. Okay, and in that case only the net flow through the channel between the channel would be equal to 0 when P is equal to -3. Okay.
Okay, sir.
Priyanka, is that clear?
Yes, sir.
Okay, so let me just as I've told you that I've told you a bit before that playing with the value of P will give you different velocity profiles with different maximum at different points. So I've just took some time and plotted the value of the plotted the velocity profile for different values of P. Is it visible?
Yes, sir.
Okay, so this one basically the x direction basically gives us the velocity uy, and the y direction gives us the y direction coordinate. Okay, the y coordinate. If we plot that, I just substituted I just plotted the velocity profile in terms of y using a software, this using MATLAB. So for different values of P, I have plotted a velocity profile. So you can clearly see if I play with the value of P, my maxima point also changes. So in this case, the maxima, see if P is smaller than 1, the maxima lies at the upper plate itself, right? If P is greater than 1, you can clearly see the maxima has shifted and has reached to a point here. And if I would have taken a value, other value, say if P equal to 2, you could have seen that the velocity profile would have changed like this. Correct? Similar to that, if we take the negative values of P, you will get some velocity profile of such these forms. Okay. The interesting case is for P equal to 0. P equal to 0 basically means that the pressure gradient in the between the channels is 0. So what is that case basically referring to? In the question before, if we remove the pressure gradient and only the upper plate was moving, what kind of flow does it represent?
Pure shear driven cold flow.
Yes, only a pure shear driven cold flow. So the velocity profile would be a linear one, where u of y would be equal to capital U y by h, which is a linear velocity profile. And that's why it clearly shows when pressure gradient is 0, we will get a linear velocity profile. Is that clear?
Yes, sir.
Okay. Again, for the special cases that we have discussed, we have seen that. Okay, I have done a mistake here, guys. This should be equal to +1. Okay, this is +1. That cases where the net shear stress at the upper plate is 0, where P was 1, right? So this is the velocity profile. This kind of velocity profile would cause the shear stress at the upper plate to be equal to 0. Similarly, for P equal to -1, it is P equal to 1, then P equal to -1 is given by the orange velocity profile, which will create a 0 shear stress at the bottom plate. And finally, for P equal to -3, this is a special velocity profile which would cause the net flow between the channels to be 0. For P equal to -3, we will get a mass flow volume flow rate that will be equal to 0, and that thus there will be no flow between the plates for the given conditions. That is, the upper plate is moving and also there is an applied pressure gradient. You can see Priyanka, you are mentioning about equating the pressure and the velocity, right? See, here in this case, the upper plate is forcing the plate to move in a positive x direction, that is dragging the fluid elements towards the positive x direction, and thus this part of the velocity profile, like these fluid flow elements are being dragged to the positive x direction, right? But for P equal to -3, we encounter an adverse pressure gradient that creates a flow towards the negative x direction, right? And when these two factors balance each other, there is a net 0 flow between the channels, and thus the velocity profile. Now, can both of you understand the physics, how the velocity profile tells you the two opposite effects that acts on the flow that thus results in a 0 net flow between the channels. The adverse pressure gradient in this part is dominating this and thus a reverse flow in this direction, and the upper part where the upper plate is moving, that's why it is dragging the flow towards the positive x direction. Is it clear? Can you see now what was actually happening?
Yes.
Clear, sir. So for question number 5, that one option which said for pressure less than 0, the flow reverses near to the fixed plate. That option is correct, no, sir? The last option, I think, for the question number 5 which we discussed.
Okay, let me go through it. This is question number 5, right?
Question number. Not 6 then. Our question number 6.
Yes, here, you can see there's a backflow.
When P is less than -1, a backflow occurs near the fixed plate.
Yes, you can see here also. I guess I took a value of less than -1. You can see there is a backflow, right?
Yes, sir.
Here you can see here still there is no backflow. If you draw a straight line from here, I am sorry for the line. It will I can draw it, I guess. If you draw a straight line from here, you can see there is no backflow yet, right? For P equal to minus 0.75, but for P equal to minus 1.5 there is a backflow, right?
Yes, sir.
Yes. So I guess the concepts were clear. I was able to help to understand by these plots. So okay then, thank you. That's all for today. Hope that I meet both of you in the last session, that is in this Sunday, or if it is by some means shifted to Monday, I will notify you. You will be notified. So I hope to see both of you in the last session. Okay.
Okay, sir.
Yes.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Okay then.